Okay? All right, so from our activity, right, we just discovered a way in which you can count something that is small. Okay? Well, atoms are the ultimate small thing. And so that's what we're learning about today is how did scientists choose to group them in a way so that we can measure them, okay? Our objective, we have two objectives. Our first one is I can understand the importance of the mole unit in chemistry, okay? So in chemistry, obviously we deal with very small things. And I'll be honest, using the phrase very small doesn't even do it justice for how small atoms are. And we'll kind of dig into that as we go throughout today. It's impossible to count them by hand. Up until just recently have we actually been able to see them. So we do have microscopes these days that can see atoms. It's not a type of microscope you like look through, but from the microscope it can generate an image that we can see atoms. But even then it's impossible to count. Does anyone know how long it would take to actually even count to 1 million? Like how many days? Right, like it would take for, I was just about to quote it, but now I feel like I'm going to misquote it. I saw it the other day on the aquarium wall. It said, do you know how long it would take to count to 1 million? But it was like over 2 months, right, of you nonstop counting every second of every day. So we just can't, right? And so obviously we need a way to group them. And so what scientists decided, I'm going to come back to that video later. Oh, hold on. I feel like I missed a slide. Do you feel like there's something missing?
I don't know. We should have that eventually.
Yeah, I don't know where it went. I'll write it down. Okay. And so scientists decided, based on math and proportions, to use the word mole as the unit to group atoms. Okay, now once again, units are just arbitrary. They're just decided like, hey, let's call it this. I don't really know why it's called a mole. It has nothing to do with the cute little creature. Okay, but what it's equal to, so write this on that first blank right there, okay, is it is a counting unit. Okay, that's your first blank. The first thing to recognize is a mole is a counting unit, just like a dozen, right? It just counts items. A mole is also counting items, okay? It's also known as Avogadro's number because he was the scientist who discovered or generated this mole, this unit. Avogadro was his name. So sometimes we call this number Avogadro's number. And what it's equal to is 1 mole is equivalent to 6.02 times 10 to the 23rd. Raise your hand if you feel like you can explain to someone what this means, like when we have times 10 to the 23rd. Raise your hand if you feel like you could explain that. I just want to see like our understanding of scientific notation. Drew, could you give us a quick explanation?
Yeah, like that 10 to the 23, that's 10 with 23 zeros there, so it's 602.2 octillion.
Good job. Yeah, so imagine we write it this way because it's such a big number. Instead of writing all those zeros, we just group them in this way, okay? And we're going to watch a little video that kind of shows what this number actually looks like in real life and how big it is, okay? I just have to switch over because my sound wasn't working on my iPad, so let me switch to my computer really quick. Okay. Maybe, hopefully our sound will work now. I don't hear any sound. Okay, hold on one moment here. not, I'll just summarize the video for us. Or we could watch it with subtitles.
Digs holes in the ground and destroys gardens. And some of
Can
you
you
might
even
be
hear
thinking
that? It's only coming out of my
under
computer.
its face with hair sticking out of it. Well, in this
Back
case,
table, can you hear
mole is a
that?
concept that we use in chemistry
No.
to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amadeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Fortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the molar. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs.
Okay, I'm gonna pause for a second
When you go to the
here.
grocery-
Okay, so a mole is a crazy big number, right? Like, did you hear that last statistic? $1 million a second, your whole life, and you'd still have 99% of your money left over, right? Like, it's huge. So I want us to think for a second. Don't say anything out loud, and then I'll hear some ideas. Why is the mole so big? Right? Why is it so big for this unit? Right? We talked about how units are just arbitrary. We pick them to group things. But why is the mole so big? Don't say it, but think for a second. Raise your hand if you have an idea willing to share. Sasha, what do you think?
Because it's on a molecular level when molecules are extremely tiny. So then when you're doing the mole size, it's not as big as a whole basketball.
Good, right? The mole has to be so big because atoms are so small, right? If we group them by the millions, wouldn't be able to see them. Group them by the billions, still can't see them, right? Like, they're so small, we had to group them by this crazy big number so that it's actually something I can measure out and see, right? It's the way the mole is the thing that bridges this gap in chemistry of what I can't see to now something I can see. Okay? Now, obviously, we can't count atoms to use them, so let's look here, and then this will lead to our last little topic of how then do we actually measure
Grocery
them.
store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is, anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
Okay. So this last part that we'll get into is, obviously we can't count out atoms. They're too small and a mole is too big. So it's done very similar to the activity we did where it's done by mass. So we're going to learn about something here. Let me switch back to the iPad called molar mass of how we can measure out amounts of atoms. Okay, let me close that. Open this. Okay, so like we said, a mole is a counting unit like a dozen, okay? But unlike being able to count a dozen of things very easily, we can't count to a mole of things, and so we're going to be doing it by mass, okay? So molar mass equals the mass of 1 mole of a compound. Mass is measured in grams, so molar mass is can be 1 mole of anything. Okay, we can find this by using the periodic table. So our periodic table is going to be our key to finding the mass of our elements. What's cool about the periodic table is not only does it tell you the mass of a single atom, but it's proportionate to a mole. Okay, so everyone take a highlighter for me, and I want you to highlight this number right here on our picture. Okay, highlight that 12.011. Yes, Sasha? Sorry, let me look at up here. Right under molar mass.
Yeah.
So molar mass is the mass of 1 mole of an element of compound, which is moles per gram are always the units. Mole per gram, yeah. So this number right here, this 12.01, does tell us the mass of 1 atom of carbon, but in a unit of an AMU, and it's proportionate to 1 mole of a substance now in grams. So the molar mass of carbon is just 12.01 grams per mole. Now for simplicity, we're going to round all decimal places here to 2. Okay, so that's why I dropped the last one. So for just every time you're doing your homework, you can always round to 2 decimals. But if you want to highlight and then draw an arrow to remind yourself where that came from, we're just looking at the periodic table. So same thing, if I wanted to find aluminum's molar mass, I'd come to my periodic table, find aluminum, 26.98 grams per mole. For a smiley face, find zinc really quick and write it down. Give me a pencil drop when you found it. The hardest part of today's homework should just be finding things on the table. That's pretty much all we're doing, but sometimes it can take a little while to find them. If you have 65.38, give yourself a smiley face. Okay. Now, the only added step to this is when it's not an element, but it's actually a compound. So, for example, water, right? Water is H2O. It's not directly on the periodic table, but it's made up of pieces that are. So we just have to add those pieces together, right? So remember, the subscript here means you have 2 of those, and then plus 1 of those. So the total molar mass of water would be 18.1 gram. Okay? Let's try a few problems together, and then I'll have you try some on your own. Okay? So let's find the molar mass of table salt. Okay, so I'm going to find sodium on the periodic table. 22.99. And then I need to find chlorine on the periodic table. Say that again. Atom. Because think of it as just all the different pieces that it has. Chlorine is 35.45. Those are my individual masses. So to get the total, I would add those together. And I didn't do it beforehand. 58.44. And then always label your final answer with grams per mole. Questions on how I got that? So if this little container right here is 1 mole of NaCl, 1 mole of table salt, how heavy is it?
58.44
Say it louder, Kens.
58.44.
Yeah, that's how I got this, is I measured out 58.44, and I know that's equivalent to 1 mole of a substance. Questions on that? Okay, let's look at the second one together. So sometimes compounds here, right, as we see, have parentheses. There's a few ways you can think about this, but you just need to make sure you take into account all the pieces. Okay, so if I break this down, so let's do magnesium first. So I'm going to do them in different colors here to help me see. So magnesium, find its mass, 24.31. And I need to multiply that number by 3 because there's 3 mg's in the compound. So 72.93 would be the total amount of magnesium. Okay, now for my phosphorus here, the parenthesis, just like in math, we need to distribute. Okay, so let's find the mass of phosphorus, 30.97. And then I'm going to times that by 2. Because there's 2 phosphoruses in there. 61.94. Now for my oxygen. Oxygen has a mass of 15 I guess it rounds up to 16 when you only keep 2 decimals. And then we have a 4 inside the parenthesis, a 2 outside the parenthesis, so that would be a total of 8 oxygens. Because you got to multiply it in. So 128. And then I'm going to add all these up together. And I got 262.87 grams per mole. Questions on calculating molar mass? Once again, just taking all the pieces and adding them up. Okay, since it's a Wednesday and we're a little shorter on time, I'm going to let's skip the you do, and the you do will be your homework because you're going to practice there anyways. So let's go to the homework packet, and it's just one-sided. I do have to see some amount of work to receive credit, because otherwise I don't know the difference of you just copying it down from somebody else. Okay? But it's just that one-sided, 8 problems practicing molar mass. Okay?